The name bipolar implies in your bipolar junction transistor, the current is constituted by two types of carriers, that is bipolar, that is positive charges and negative charges. Positive charges we'll call it as holes, negative charges electrons. Positive and negative. Hence the name bipolar junction transistor. Main application of bipolar junction transistor is in amplifiers, widely used in amplifier circuits, and of course in switching circuits as well as amplifiers. We are using bipolar junction transistors, right? BJT is a three-terminal device. Let us call it as emitter, base, and collector. Emitter, base, and collector. It has three regions. If the transistor is falling in the category of N-P transistor, we have three regions, two N regions and one P region. Of course, the structure will have two junctions, two PN or NP junctions. So the transistor, bipolar junction transistor, is a bipolar device, implies it uses two types of carriers, and it has three regions and two junctions. With respect to the area of emitter, base, and collector, W implies width of the region. So WC is larger than WE, and base area or width of base region is very less. WC is made wider because in amplifier circuits, collector region is operating in reverse mode, or collector base junction is reverse biased. Due to the collector current flowing through the reverse biased junction, there will be a heat dissipation in the collector region because the carriers are accelerated and flowing through this collector region that is reverse biased. So there exist atomic collisions that will increase atomic vibrations, that in turn increases the heat in the region. So to dissipate maximum heat, we are ensuring width of or area of collector region is much larger than the other regions, emitter and base, right? With respect to carrier concentrations or doping concentrations, emitter is heavily doped, so I will use plus plus sign. Plus plus implies heavily doped. Base region is moderately doped, so I will use a P plus simple. And the collector is very lightly doped, so I will use a minus simple. In your NPN or PNP transistor, doping concentration at emitter region, that is N is number of carriers per meter cube or centimeter cube, in emitter region is always greater than number of carriers or doping concentration in the base region, and that is in turn greater than number of doping in the collector region. Or emitter is heavily doped, base is moderately doped, collector is lightly doped. Please don't confuse. Base is moderately doped, or doping concentration at base is greater than doping concentration at collector. Right? And the doping concentration at emitter region will decide the current gain of the transistor, namely beta. Doping concentration at emitter is more because to improve the current gain.
Sir, base അല്ലേ lightly doped ഉണ്ടാവുക?
അല്ല, അതുകൊണ്ടാണ് ഞാൻ വീണ്ടും പറഞ്ഞത്, please don't confuse. Base is more heavily doped than your collector. And width of base is least, or area of the base is least. Least doping concentration is at collector, NC. Highest doping concentration is at emitter, switchium, and base is moderately doped. Clear? So please don't confuse. Base is more heavily doped than collector region. And that is true for both PNP as well as NPN transistors. Now change. All these parameters are true for PNP transistor also, emitter, base, and collector. Right? So next we will see what are the different possible modes of operation. As we said, we have two junctions. One is emitter base, the other one is base collector. So two PN junctions, base emitter and base collector. We know that PN junction is a binary device, can be either on or off, reverse biased or forward biased. So total 4 combinations are possible. Both can be reverse biased, reverse biased and forward biased, and reverse biased. Both are forward biased. Right? The mode with both are reverse biased implies a cutoff mode or cutoff region of operation. Both forward biased implies a saturation mode or saturation mode of operation. These two regions are common in switching circuits, or if you are operating your transistor as a switch, it will switch between cutoff to saturation or saturation to cutoff, two states. And of course, one is cutoff mode. For a switch, cutoff off implies zero current. So the transistor current IC equal to 0 or IE equal to 0. Both currents are 0. You can say that IB also equal to 0. All currents are 0 when it is in cutoff mode or open circuit, acting as a switch position 1 and 2. One corresponding to cutoff, off position, or open circuit. The second one, base current, emitter current, collector current, all will have maximum value, and that maximum value will depends on the circuit components present along with your transistor, right? So reverse biased, both are reverse biased cutoff, open condition of a switch, both are forward biased saturation, closed condition of a switch, right? The other two modes, base emitter reverse biased, base collector forward biased, and base emitter forward biased, base collector reverse biased. So the third mode, base collector reverse, base emitter forward, we'll call it as an active mode of operation or linear mode of operation, or the transistor act as an amplifying device, right? So if your base emitter is forward biased and base collector is reverse biased, your transistor is performing a function. That function is called amplification, and that should be linear. Linear in the sense, if you are giving a sinusoidal signal, output should be a scaled version of. There won't be a distortion like this we observe in the Clipper circuit. So shape should be same, amplitude will be scaled by k times. So size same, shape different, size or different amplitudes. That's why it is called linear. Another name is active mode, acting as an amplifier, right? And the other region is called just the inverse of your amplifier mode, because instead of forward biased here, base emitter, it is in reverse biased mode. Base collector, amplifier mode, reverse biased, here it is forward biased. So we will call it as an inverse active region or inverse active mode. And of course, it's a non-linear behavior. It's a non-linear, and it's not an amplifier. It acts as an inverse operation of amplifier. That is nothing but attenuation. Attenuation, right? Inverse of amplification is attenuation. So attenuation, nonlinear, inverse active mode when base emitter is reverse and base collector is forward. So application of switch, first and last, saturation and top, and amplifier active mode, linear mode, inverse active, attenuation or non-linear behavior of your bipolar junction transistor, right? Next we will see the circuit simple of your bipolar junction transistor. So you should understand why the symbol appears for an NPN transistor like this. This is a symbol of NPN transistor. This is emitter, this is collector, this is base. Right. So let us see that. As we discussed, it's a 3-layer device. NPN device. Right. If we are operating, this is emitter, this is base, this is collector. If we are operating in active mode, let us say active mode, we have to forward bias this region And forward biasing by applying negative here, positive at base, because base is a P region. So I'm applying a positive bias. And I have to reverse bias the collector base region or base collector region. Collector is N, so I'm giving a positive to reverse bias it, negative here, and base is common connected to ground. Right? Let us assume it is an NPN transistor. N region implies it will have a lot of, N type implies a lot of electrons, right? P region implies it will have a lot of holes, right? Since this junction is forward biased, N connected to negative pole, and N region has a lot of electrons and few number of holes. Few number of holes. P region has a lot of holes and a few number of electrons. Since emitter base junction or base emitter junction is forward biased, N region is connected to negative pole that will repel the majority of electrons present in the N region. In the N region, we are having more electrons implies majority of carriers or majority carrier is electrons. Whereas in your P region, majority carriers are holes. Right? That's quite simple. N for negative electrons, P for positive holes. Charge of an hole is a positive charge. Charge of an electron is a negative charge. So all electrons, majority of the electrons will repel by the negative pole because charge of an electron is negative. All electrons repelled by this negative pole will travel towards base collector region. And those electrons repelled by the emitter region is collected by the positive pole connected here because a positive pole will attract electrons. So all electrons are collected by the positive pole. That's why this terminal is called collector. This is called emitter because it is emitting the majority carriers. In this example, they are electrons. Majority carriers at emitter are electrons. So emitter region emits the electrons in this example, and the collector region collects all the emitted electrons coming to the collector region. So here electrons are emitted, electrons are moving towards right, implies this negative pole should supply enough number of electrons so that these electrons will replace the electrons migrated towards the collector region. Right? So electrons are actually flowing into the emitter terminal. So the conventional current is just opposite to the flow of electrons. So emitter current IE is flowing out of the emitter terminal. Emitted electrons are migrating from emitter region to the collector region, and finally it is collected by the collector supply, positive rail. And those migrated electrons should be replaced by the source connected to the base emitter region. So negative pole of the source will supply electrons into the emitter. So actual current flows out of emitter just opposite to the direction of the flow of electrons. So that's why emitter you are having a outward arrow. Implies emitter current leaves the emitter terminal. Right. The collector collects the electrons. So electrons are moving away from collector, right? Moving away from collector. So the flow of electrons away from collector, it implies the actual current flows into the collector. The electrons are moving away from the collector implies actual current is just opposed to the flow of electrons. So collector current flows into the collector. So this is my collector current, right? And I have one more terminal called base terminal, and we didn't discuss anything about base. Well, during the migration of electrons from emitter region to collector region, electrons will come across a majority of holes in the p region because it's a p-type region. A positive charge electrons will meet a negative charge, a positive charge holes will meet a negative charge electrons. So they will recombine each other. So there is a shortage of holes in the p region. So that p region number of holes are fixed by the doping concentration at base NB. So the recombined hole should be supplied by the supply rail positive here. So it should supply enough number of holes. So holes flows into the base is supplying holes. So conventional current is same as the direction of flow of positive charges or holes. So your base current flows into the base terminal, right? So for your NPN transistor, collector current flows in, base current flows in, and emitter current leaves the collector. If you are treating this as a node, like this as a node, KCL should be valid at that node. That implies total emitter current should be the sum of two currents, incoming currents, IC and I. So emitter current is the sum of base current as well as collector currents. Right? So circuit simple, total general current equation in terms of IC, IP and IE. Here, let us look into the ideal behavior of an NPN transistor. What is the ideal behavior? Ideal behavior. If the transistor is ideal, what all are the factors to be equal to 1, equal to 0, equal to infinity? Let us see that. Ideal behavior of an NPN transistor. It's clear that if the transistor is ideal, all the emitted electrons should come at collector. All the emitted electrons should collect by the collector rail if the transistor is behaving as an ideal. Right? So, if all the emitted electrons are collected by the positive rail of a collector supply, implies emitted electrons will be replaced by the negative pole here that constitute an emitter current. And if all those emitted electrons will collected by the collector current, implies the same collector current flows into the collector. Because if 100 electrons are emitted and 100 are collected by the collector, that creates an emitter current corresponding to flow of 100 electrons here. because that 100 electrons should be replaced by the negative pole here. And those 100 are reaching a collector that will be collected by the positive rail. So that creates a current flow corresponding to 100 electrons. So if all the emitted electrons are collected by the collector pole, then you can say that IC will be equal to IE, and that is ideal behavior of your transistor. And of course, if all the emitted electrons are collected by the collector, that implies no recombination in the base region. Not even a single hole is recombined by the electrons, and always the number of holes remains as NB in the collector region. Sorry, in the base region, equal to the doping concentration in the base region, NB. So this positive pole need not replace the holes, implies there won't be a hole flow into the base, implies base current will be 0. And when base current equal to 0, your collector current should be equal to emitter current as per KCL around the node, at the transistor node. So an ideal transistor implies its a collector and emitter currents are same and it won't have a base current. That is the ideal behavior of a transistor. Okay. And the transistor, bipolar junction transistor, falls under the category of a voltage controlled current source. Please don't confuse. It's not a current controlled current source. It's a voltage controlled current source because there should be a voltage to turn on the respective regions, and output can be modeled by a collector current IC that is proportional to number of electrons emitted from the emitter side. That in turn depends on the magnitude of base emitter supply voltage. So it's a voltage controlled current source. The earlier device what we learned in the class was op-amp, that is voltage control, that was voltage controlled voltage source, whereas your bipolar junction transistor is a voltage controlled current source. So please don't confuse, it's not a current controlled current source, it's a voltage controlled current source. And while discussing op-amp, we understood that since it is voltage controlled, it implies there is no current to the input side. So Rin was ideally infinity. Output side was a voltage source, so R out was 0 ohms. Whereas in your transistor, it's a voltage control device, so Rin should be ideally infinity. Practically it is not. And output impedance ideally should be, it's a current source. If the current source is an ideal current source, implies all the currents should be transferred to the load even in the presence of input impedance. That is an ideal current source. This current should be always I, same as this. So to transfer the entire current to RL, this Rin should be infinity. When it is open, that is infinity, then only the entire current will flow through the load. Right? So ideal current source implies infinite impedance across the source. So output impedance R out is ideally infinity. Practically it is not. So ideal behavior of an BJT is voltage controlled current source. So Rn is infinity. It's a voltage controlled device. No current ideally. Practically it is not possible. And output is a current source. So R out is also infinite. An op amp itself, a transistor itself. If you're clubbing op amp or transistors along with the resistors and other components, its behavior may not be always voltage control voltage source and voltage control current source. So individually they are voltage control voltage source and voltage control current source. Like okay. So our fundamental equation was emitter current is equal to collector current plus base current, right? Before that, we have to on the point, right? Any doubts, any issues?
സർ ഒരു ഡൗട്ട് ചോദിക്കട്ടെ ഈ ബി ജെ ടി
Yes.
എന്തുകൊണ്ടാണ് കറണ്ട് കൺട്രോൾ ഡിവൈസ് എന്ന് പറയുന്നത് ഈ എഫ് ഇ ടി ബി ജെ ടി കമ്പാരിസണിൽ അങ്ങനെയല്ലേ പറയുന്നത്
A comparison like compared to FET, bipolar junction transistor has non-infinite Rin, whereas your MOSFET or FET will give you Rin. Ideally, it's equal to infinity. In practical sense, also it is infinity only because we are having metal oxide. There is no current into the gate terminal.
ഓക്കെ സർ
Right? So you can call MOSFET also a voltage controlled current source. There is no confusion in the case of MOSFET, but you will have a confusion in the case of BJT because in BJT we are having a base current IB. If base is your input terminal, you'll have a non-zero current and Rin need not be infinity always. So ideally it is not a voltage current voltage controlled current source, but IB is extremely small normally in microamperes, so we can approximate your BJT also a voltage controlled current source, or the other way a source is required to control the operation of a bipolar junction transistor, right? Okay, Anna?
ഓക്കെ സർ
Okay. So before that, we have to discuss one more thing. I said all the emitted electrons are collected by the collector supply voltage in this example, and all electrons should cross the junction called base collector junction. If the base collector junction is forward biased, I'm drawing a base collector junction here. Transistor was NPN, so this was base, this was collector. If this is forward biased, let us say forward, it's not forward biased in our example, it is reverse biased. Active region, active mode we have taken. Suppose it is forward biased, then you have a majority of holes here, majority of electrons here, right? And if the junction is forward biased, the majority of holes will be rejected by the positive pole. So the holes will move towards right. Electrons will be rejected by the negative pole. Electrons will flow towards left. And the conventional current is from left to right. Whereas in your P region, majority are holes, there will be a few number of electrons or minority carriers. Here, few number of holes, majority carriers. Few number of holes, minority carriers in the N region. These minority carriers holes are attracted by the negative pole because holes are positive charge attracted by the negative pole, And these negative charged minority electrons will be attracted by the positive pole. Or the other way, a positive or a forward biased PN junction, you can expect a one word question from this. Forward biased PN junction will easily crosses, or the forward biased PN junction will help the majority carriers to cross the junction, and the same forward biased junction will block the flow of minority carriers. Is it correct? Clear? Holes are easily crossed by the positive pole here. Repelled, crosses, attracted by negative pole. Electrons repels by negative pole. Majority of electrons and collected by the positive wave. So majority carriers are easily crosses the junction when it is forward biased, whereas minority carriers are not crossing the junction. They are blocked by the electric field induced in the junction, or in general way the minority carriers are not allowed to cross the junction when it is forward biased. Is it clear? Right. Keeping this point in mind, if base collector junction was forward biased, right? If it was in forward biased mode, actually it is reverse biased active mode. So if that is forward biased mode, the emitted electrons will come at the base region. At base the electrons are minority. If this is forward biased, that will block the minority carriers. So you won't get emitted electrons at collector, right? Whereas if the junction is reverse biased, PN junction, P to negative, N to positive, reverse biased, that will attract majority holes to here, majority of electrons to positive, and it will repel the minority electrons in the P region, minority holes in the N region. So a reverse biased junction will not allow a majority carrier to cross the junction, whereas a reverse biased junction will allow minority carriers to cross the junction. So the emitted electrons in the case of an NPN transistor are minority carriers in the base region. To pass those minority carriers came from the emitter region. The second junction or base collector junction should be reverse biased. So that's why we are reverse biasing. Or the other way, the emitted electrons are proportional to the voltage here, and that proportionality is exponential because diode current is exponential related to the diode voltage. So it is proportional to exponential of VBE, number of electrons emitted by the emitter region, and the collector current also should be proportional to the same number of electrons, or proportional to exponential of the voltage applied at the base emitter region, if and only if the entire emitter electrons crosses the PN junction and collected by the collector supply. That's why we are keeping second region reverse biased, and first region base emitter forward biased. That's why you are having a linear response, because even though it's exponentially related, you can approximate it as a linear case when VB is very small. That we'll discuss during in the class of amplifiers. So if exponential VB is can be approximated as a linear, implies this emitter current is linearly proportional to applied voltage. Also, collector current is linearly proportional to applied voltage. That's why we have written a linear mode when base collector is reverse biased. And that linearity will not valid if that junction is forward biased. Right? Of course, when base emitter is reverse biased, as we discussed, the current is not exponentially proportional. If it is reverse biased, current is ideally zero, because exponential minus will be very, very less value. When it is reverse biased, it is minus. Right? So that's why we have written linear mode in the case of amplifiers. When base emitter is forward, base collector is reverse. One more point, forward biased junction will easily passes the majority carriers, forward biased, and completely blocks the flow of minority carriers across the junction. Whereas a reverse biased junction completely blocks the flow of majority carriers and it easily allows a minority carriers to cross the junction, right? And two models, voltage control voltage source for op amp and voltage controlled current source in the case of a transistor circuit. Right, so let us have a look into the current equations. Emitter current was equal to IC plus IP. If you are dividing your current equation with both sides with I, you can divide with any. Then let us divide it with IC, that will be easier. Get 1 plus IB upon IC. Here we have two definitions. Collector current is nothing but alpha times emitter current, and base current is nothing but collector current is nothing but IC is nothing but beta times base current. Right? This alpha measures how many number of electrons are collected by the collector. If it is ideal case, ideal transistor behavior, we said that all the electrons are reaching at a collector. So IC equal to IE. So in ideal case, your alpha value will be equal to 1. In an ideal transistor, alpha is 1. And beta value, ideal case, IB should be equal to 0. But there should be a finite non-zero value of IC. And beta should tends to dot infinity. Or the other way, from the same expression, beta can be expressed as IC upon IP. Ideal behavior implies no recombination, no base currents. So IB equal to 0. So something upon 0 will give you infinity. So beta is infinity in an ideal transistor, or base current equal to 0, and alpha equal to 1, or the other way, collector current is same as your emitter current. Right. So we have two definitions here for alpha and beta. Beta is nothing but collector current upon base current. Alpha is nothing but collector current upon emitter current by using these two definitions. And IE upon IC will be 1 upon alpha. Right? 1 upon alpha. 1 upon alpha. That's equal to 1 plus IB upon IC is nothing but 1 upon beta. So 1 upon alpha is nothing but beta plus 1 upon beta is 1 upon alpha. Implies alpha equal to beta divided by 1 plus beta. Right? To demand alpha equal to 1, beta should goes to infinity in the ideal case. Right? Using the same equation, if you are placing it as 1 by alpha minus 1 equals 1 over beta. I'm taking this one to left side. So 1 minus alpha upon alpha equals 1 over beta. That will give you, taking the inverse, beta equal to alpha upon 1 minus alpha. So as alpha tends to infinity, alpha tends to 1, 1 minus 1 denominator will be 0, beta tends towards infinity. So these two are the relations. General value of alpha is always less than 1, beta is always large, very greater than 1. Ideal behavior, zero base current, same collector and emitter currents, alpha equal to same, and beta is infinite. Beta is right. So ideal behavior also you should keep in your mind. Right? Clear? And why we are reverse biasing base collector region? To make it proportional to the applied base emitter voltage. So that emitted electron from emitter region should collected by the collector. So base collector junction should pass all the electrons emitted from the emitter region, and the emitted electrons are minority carriers in the base region. To cross these minority carriers, we should reverse bias the base collector junction. Right? Clear? Any doubts? Okay. All right. Let us have a look into the behavior of IC and VCE. So this is my emitter, base, collector. I am forward biasing my emitter region, which is N, P, N transistor as we discussed earlier. And I'm reverse biasing my collector, base region. Right? And I'm making my emitter as a reference. So VCE is nothing but sum of these two voltages, and that I'm taking on my x-axis. This is correctly current I. Right. Once this voltage VBE, this one, is fixed, the number of electrons emitted by the emitter is fixed. So I'll have a constant current, because if this is fixed, number of electrons emitted by emitter is fixed, and the number of electrons collected by the collector hole is also fixed. Right? If I am varying this voltage source and I am increasing my VCE. So this ender voltage is nothing but VCE. If I am increasing this voltage between collector and base, my VCE will increase. And if I am increasing it again and again, the base collector junction will break down after some voltage. We'll call it as VBR, breakdown voltage. And collector current increases excessively, transistor will get damaged. And as long as this is forward reverse biased, base collector is reverse biased, I will have a constant collector current because the number of electrons emitted is constant due to a constant VBE. Suppose my VCE is in the neighborhood of, let us say, 0.3 volts, right? So I have to decrease this value so that VCE will come nearly 0.2. Then to forward bias, to reverse bias a PN junction, we should have a PN value. To reverse bias it, you should have a positive negative value greater than, normally it is 0.7, right? So if this is coming less than that, this junction will become less reverse biased, right? If you are decreasing this voltage source, that will anyway decrease your VC value. So if you are decreasing this base collector region will become forward biased. When this junction becomes less reverse biased or forward biased, that will block the minority carriers crossing the second junction, that is electrons emitted from the emitter region, right? So the number of electrons collected by the collector supply will get decreased because we are reducing the reverse bias by decreasing this voltage. And if this is negative, this is anyway positive, greater than 0.7 volts. This is negative, VCE will become less than 0.7. Suppose this is 0.7. This is at 0.7. This is negative, implies VCE will become less than 0.7. And if this is minus 0.7, base collector junction potential is minus 0.7, or this way, forward biased, positive, negative 0.7, that implies minus 0.7 with other polarity. Then we'll have a VCE 0. Usually, the doping concentration of emitter and collectors are not same. So to forward bias the base collector junction, we need not go for a 0.7 volts. A 0.5 volt or near values will be more than enough to forward bias a PN junction when doping concentrations are very less. Please don't confuse. To forward bias an ordinary PN junction, we require 0.7 volts. If you are varying that doping concentration, you need not wait for 0.7. So this collector is heavily doped N minus. So this junction will become forward biased earlier. So 0.5 will be enough. So if this supply voltage reaches minus 0.5 or 0.5 positive with respect to N is more positive with respect to N by 0.5 volts, that junction forward bias, then that completely blocks the electrons coming from the emitter region because they are minority carriers for base collector junction. That is now that is now forward biased. So that will completely block the minority carriers, that is electrons coming from the emitter region. Then I will have a sharp decrease in current that happens when approximately VC is minus 0.7. Anyway, VB I'm keeping as same 0.7 implies that will occur when saturation will occur when VCE equal to a voltage. How much it is? A voltage. VCE equal to a voltage. That value is nothing but 0.2. That 0.2 is the sum of this 0.7 with a minus 0.5. So 0.7 minus 0.5 will give you 0.2. That voltage we will call it as VCE, voltage between collector and emitter, VCE saturation. Why it is called saturation? Normally this is forward, this is reverse bias. So we decreased this source voltage, DC source value. We made it negative, negative 0.5. That time it completely blocks the currents from emitter due to currents due to the emitted electrons from emitter region, and none of the electrons are collected by the collector region, right? Only a current corresponding to majority carriers in the regions P and N regions will flows across base collector junction. Since the doping concentrations at base and collectors are extremely low, that current will be comparatively very less than your actual emitter current. So we are assuming it as it's very low or ideally zero. So this voltage we will call it as VCE sat. VCE sat. That's why you are observing a decrease in the characteristics of your IC versus VCE characteristics. We are selecting IC versus VCE is due to nothing but IC is the terminal current and VCE is the terminal voltage of your device or output characteristics. Output terminal current versus output terminal voltage. So in this region, it is clear that second junction is reverse biased, first junction is forward biased. So we will say that the transistor is in which mode? Active mode, right? Active mode. In this region, the second region becomes forward biased. So we'll say that the transistor is in which mode? Saturation. First region is anyway always forward biased. Otherwise, no emission of electrons, no currents. So in your output characteristics, you'll have active region for larger values of VCE that ensures a reverse bias of a base collector region. If you're decreasing that VCE to a particular value, usually it is VCE equal to 0.2. If you are bringing less than 0.2, your current is getting decreased. Current is getting decreased. And it will go to negative also. Why it is going to negative? Turning on this junction will create a current flow. Positive P, holes will move towards right. N region, electrons will move towards left, right? Towards left. No current constituted by the emitted electrons from the emitter because the second junction is forward biased. It completely blocks the minority carriers. And that current, holes flowing towards right. So holes leaves the collector. Whereas initially in active mode, you should recall that collector current flows into the collector. But if this junction is forward biased, collector current leaves the collector, right? So the polarity is different. It goes to even negative. That's why characteristics is extended beyond zero value to negative. So the current is flowing to the other way, corresponding to a turn on of second region. Is that clear? So the point we have to remember is approximate VCE value corresponding to saturation turning on both junctions is nothing but 0.2 volts. Right? Until that, we'll have a maximum current in one particular direction. After that, it changes the direction if VC is negative. Is that clear? Any doubts? So you should remember the active region and saturation region, and here we are using it as an amplifier. That is clear. Right, and the cutoff region is not visible here because we are not reverse biasing base emitter. Is that okay? Any doubts? So that is a VI characteristics. And I will quickly go through the PNP transistor also with respect to its circuit symbol. Let us call again emitter, base, collector, and the transistor is P and P. We should forward bias it, and we should reverse bias the other junction to operate it in active. Right? So this positive pole will repel the holes. Those repel holes will pass through N region. N region. One second, battery is low. Hold a moment. Right. So holes are repelled by this battery. So that flows through base region and reaches here. So base collector region holes here are minority carriers because it is an N region, electrons are majority, and the junction is reverse biased. So those holes easily collected by these negative holes. So holes move away from collector. So collector current leaves the collector terminal. Is that clear? And holes are replaced by this positive pole. So holes are moving into the emitter. So emitter current flows into the emitter. Is that clear? Similar to what we discussed last time. And there will be a recombination of few electron and hole pairs, and this pole should supply enough electrons because N region electrons are recombined with the holes. We are losing electrons that should be replaced by the negative pole. So electrons moves into the base, right? So actual current will flow out of the base because electrons are flowing into the base. That give you a circuit symbol corresponding to your PNP transistor. This is emitter into the emitter terminal. So I is into the emitter terminals. IC leaves the emitter terminals. Sorry, collector terminal, right? And base also leaves the base terminal. Base current leaves the base terminal. So you should remember the direction of currents in your NP and PNP. Both IC and IB are into the terminals when it is NPN. When it is P and P transistor, IC and IB leaves. Right? emitter current collector emitter current PNP into the emitter NPN out of the emitter base currents out of the terminals leave in the case of PNP, whereas in the case of NPN both are entering. ഏതെങ്കിലും ഒന്ന് ഓർത്തിരിക്കുക, അതിന് ഓപ്പോസിറ്റ് ആയിട്ട് അടുത്ത് ചെയ്യുക. If you are reversing the direction, it will become PNP. Leave, in. So that is your in, leave. That's your PNP. So nothing else. All other explanations are valid for PNP also, except electrons will become holes, holes will become electrons, positive will become negative supply voltages. Right? Okay. So that is the fundamentals of your